Okay. Hello and welcome to this online training, to the second part of the training RFEM for students. I'm very happy to hold this training today. We have in Germany very nice weather, so I'm also very happy and I'm also very happy to do the training with you. So to me, my name is Daniel. For those who don't know me, I am responsible for the customer support here at Dlubal Software. So I answer different customer requests as good as possible. And next to that customer support, I am also responsible for the marketing. So especially for the e-learning platform, because there we have several videos we offer to you. So the content platform of that rise more and more. And I manage that with the help of my colleague Praxitelis, who is also helping me today with this online training. Praxitelis, would you introduce yourself, please?
Hello, everyone. My name is Praxitelis. Good morning to everyone. I will be assisting Daniel today to this training. For those of you who are new to this training, I am responsible at Dlubal for marketing and public relations. That's for e-learning. We're building up right now a e-learning platform. It's very interesting. You should definitely check it out. Also, I am responsible for online trainings and tutorials. So I will try today to answer as many questions as possible in the chat, and the interesting ones, as always, I will tell Daniel to explain them to you with the help of RFEM. So welcome, and as always, have fun.
Thank you, Praxitelis. Okay, let's go ahead. So for those who are visiting or visiting this training for the first time, here's some hints. We are using the webinar platform GoToWebinar. The control panel you see on the right side, there you have several options. First of all, you can show or hide your control panel in order to see more of your window, in order to see more of the training. Then, of course, here you have the raise hand symbol. So if you have questions or something like that, you can raise up your hand and Praxitelis will answer this question to you. Of course, here also in the question box, enter questions for you, for us, that we can answer that. And if you don't hear us, here you can adjust your audio settings. And yeah, so for those who are attending now, please raise up your hands in order to see if it works. Click this button here. Very fine. Good. So I pull your hands down again. So what's the content of this training today? First of all, we are modeling a 2D frame with a hinge column. See on the right side. In RFEM, you have the possibility to model also frame structures in combination with surface or plate structures. And then we skip to the concrete building you see also on the right side. And at the end of the training, you have the possibility to ask us questions and we try to answer them as well as possible. Good. I close my webcam, skip or jump to my RFEM program. Yeah, this was one of my student projects, a roof structure. So, a membrane roof structure. So, I create a new model in order to, where I click here, new model. And I'm sorry for that because this is in German. I have to change it in English, but first of all, I tried to enter the name. So first of all, 2D frame. I choose the right folder. Yeah. And one important thing is the model type. This should be at 2D XZ. Yeah, because we are referring to 2D frames and yeah, surfaces and plates in the plane. And we don't need any load combination, classification of load combination and load cases. Yeah, and my global Z-axis is orientated downwards, okay? I click OK. And now I'm sorry for that. I have to change my language. I'm really sorry for that. This could take a little time. So wait a minute. So when you want to change the languages, I can recommend here at the menu bar, under options, you find the tool program options. And we are here a lot of international people. So we offer the language, we offer the program different languages. Yeah. German, English, and so on, also Spanish, Italian, and so on. And I want to change it now in English. Sorry for that. Now I have to close and start this program again. So it will take some time. Sorry for that. Yeah.
Daniel, in the meantime, maybe I could show some controls on my screen.
I have prepared a poll.
Okay.
For you, and I think that's the good time for doing that now. So could you answer me maybe that poll? So especially for that attendees who are visiting this training. Okay, most of you have chosen this poll. I close this, show you the results. Yeah, and then we can see, okay, 97% of you have visited the first training. The first training was on this Monday. Yeah, it was in English. And I'm really happy that so much of you also visit this training today. So the second part of RFEM for students. And that's very good because now the basic knowledge of RFEM will be required for this training. And this is very fine. Okay. Now I opened RFEM now in the English user interface. I have here my 2D frame, and now we can start. Okay, sorry for that small break. I want to show you what we designed together. This will be this frame structure here. Yeah, so we have here some girders, also some columns, and here the hinged column with the bracing. And with RFEM, you can model also frame structures. And then we are going to make a stability analysis in order to get these buckling cases here. Yeah, good. So let's do that. First of all, I create my column. In order to create columns, you have to insert members. So I click here in the symbol bar, new single member. And because we haven't modeled or created one member yet, we have to create it again. So I click here, create new cross-section for member start. And it's useful to use this most common used cross-section here at that window, and we have to choose HEA profile. So in this case, this one. We click on that and choose here HEA profile 180. Yeah, we choose the right material. In this case, no S355. We want to have this in 235. So I have to create, or I have to modify this material. The best case, I think the best way to do that is modify that, because then we have modified this and we can use it the whole time. So click here, edit material. Open here the material library. And choose here steel S235. Yeah, it must not be at the standard group German. It can also be at the Eurocode. It has the same values, the same material properties. Doesn't make a difference. So choose here steel S235. Yeah, why 235? That's the yield strength of 23.5 kilonewton per square meter. When somebody is asking why is this the description of 235, you can answer him the yield strength. Okay, good. I choose that, click on OK. Now I have changed that to steel S235. I click on OK. Again on OK. On OK. And I make my column 9 meters high. So one way to do that is clicking on the right snapping grid point here. So at Z equals negative or minus 9 meters, or you can snap one of these grid points here and enter here the length of 9 meters. That has the same effect. Then right click, and now I want to show you the copy function. So I select this column here, right click, say move and copy, and the number of copies I set at least to more than 1 in order to copy that. And my displacement vector is also 8 meters. No, sorry, 9 meters. Oh, 8 meters, sorry, now it's right. Okay. Now I have 2 columns here. And now the next thing is to create here the upper girder. Yeah. So the roof girder or the roof beam. For that, I choose again here, new single member. And I create again a new profile, clicking here, creating new cross section. And for that, we need an IPE 270 profile. So again, here we have this IPE profiles. If you don't find that here, or if you don't find the wished profile, just open the cross-section library, for example here, and RFEM offers you a lot of different, several cross-sections. And when you want to find the eye profile, you click here. So the eye sections, click here on road and so on. I can do it like in this way, but I can do it also in the other way. Now I'm here at that window. Go here for IPE, and click here the IPE 270. If you want to see the different cross-section properties, so the values, click here about the info button below, cross-section, and now you see a lot of cross-section properties. Yeah, shear area, cross-sectional area, also the moment of inertia you see, and so on. I click on OK, again on OK, OK, and I model my girder from the left side to the right side. Good. Now, the next point is creating the slab beam here. We have also a slab beam or slab girder. It has another profile. First of all, I want to create this cross-section. I told you in the first online training that we have also the possibility to create cross-section members, model datas with the help of the data navigator, but also with the help of the tables. Yeah. Now I want to create the new cross-section with the help of the data navigator. So first of all, I choose the data navigator, go to the area of cross-section, open this tree there, and with the right click on cross-section, I say, okay, new cross-section, please. And there I create a new cross-section. In this case, again, an IPE profile, but IPE 360. Okay, click on OK, click again on OK. And now you see a new cross-section was added to the cross-section, and it's blue. It has the color blue. What does it mean? When you have some data here, model data especially, who are or which are blue, this means that they aren't used in the model right now. Yeah. But when we create a new member with that cross-section, it will jump to the black color because it is used for that model. Okay, you will see it. Now I want to create this beam girder here. So first of all, I want to create an additional node here. So with the right click on the left member, I can divide this member, and now I have the possibility to divide it by 3 options: graphically, by in intermediate nodes, or by distance. I choose by distance because now I can say, okay, here I have the length, here the member orientation, it's from the bottom to the top. I think that's pretty clear. So I have here the starting node and here the ending node. So, and I want to divide this at the height of 5 meters. Yeah, I click on OK. I get here a new node. Now I can easily create a new single member, again by clicking here at the symbol bar, new single member, and choose now the right cross-section I've created before. Click here IPE 360 and create that from that side to the other side. Good. Now we want to create again here a column. Yeah. And for that, I divide this member again. Click here, member number 5, and say divide member. But at that time, we do it graphically. Big advantage at the graphically dividing is that you can not divide just this member we clicked before, but also any other member. This is one advantage of the dividing members graphically. Important thing is to choose the right steps, the delta steps. And now I go to this member here. It refers also to the member orientation. And here is important that we divide this here at the length of 4.5 meters. So close this window. We have here this new created node, and now we have here the same cross-section column. So I click here on that cross-section on that column, and now I want to copy it by drag and drop. So click on that column or on that member, press the Control key on your keyboard, and now the left mouse, and drag and drop it from that to that node. Good. Now almost done. Now we need here a bracing. We can do the bracings manually, or we use one of the function of RFEM. You find many functions of creating or modeling something here in the menu bar. Under Tools, you find the function Generate Model Members, and at the bottom, Bracing and Cells. This is very useful for creating some models very fast. Yeah, in this case, it's not so fast, but I want to show you to that because you have also the possibility to create a lot of other things like continuous beams, 2D frames, and so on. Yeah, or arcs, circles, and so on. But I decide to create a bracing and cell. I click on that. And now, first of all, the bracing normally reacts just on tension. So if this member gets tension forces, it will react and transfer also the loads. But if the member gets compression forces, it will fail and this member wouldn't be calculated, okay? And wouldn't have any impact on the structure. So important, choose here the right member type, tension, and now also the right cross-section. I create a new cross-section. We have round steel here. Click on that, round steel. And choose the right diameter, 20 millimeters. Click on OK. Click and again OK, and now we have the right cross-section. Now we want to create here this cell, but normally you would see there a cross, but the reason why we don't see there a cross is because this cell or this rectangular isn't closed by a member. So we can create virtual lines. I click here on virtual line. Click then on OK. And now you see the cross because we closed this this cell here. And now we can say, okay, we click here, select cells, and I choose here this cell. Click on OK. And the bracing is generated. Good. Now the modeling of the 2D frame is almost done. Now we have to set our nodal supports. For that, I select these nodes here and say, okay, new nodal support. And because we are here at the 2D system, it's okay when we use here the hinged supports. I click on OK. And finally, we have to do now our hinges because here I want a hinged joint, and the same way here also a hinged joint, and that column should be also a hinged column. So I have to create hinges, and for creating hinges I refer also to my data navigator. So I go here again to the data navigator and I say, okay, member hinges. I click here with the right click, member hinges, and say new member hinge. And now this window opens, and let me explain it to you what you have to do there. If you want to create a moment hinge, so no moments will be transferred to the other member, you have to activate here VY, so the hinge. If you want to create shear hinges or normal forces hinges, you have to activate the displacements here, yeah, UX and UZ. So for that, we want to create a moment hinge. We have to activate here VY. You can do it also by clicking here one of these shortcuts or icons here, set rotational release MY, and it has the same impact. Yeah, for that I choose the VY, click on OK, and you see here now, okay, this member hinge was created, and it's again in blue, so it isn't set or it don't refers to any of these members. To change that, click here with right click, say assign graphically to members, and now I have the possibility to create it here at the beginning of one member, or when I have it here in the middle of one member, it will be created on both ends, yeah, and the same here. So I decide here for the beginning of this node, so this member hinge will be created at the end or at the beginning of this member. Here the same, and here I do also the same. I click on OK, and you see here these hinges. These are white points in my case, and these white nodes symbolize me a hinge. Good. Next thing.
Daniel, sorry to interrupt. There are many people asking about the bracing, if you could show it again.
Of course, no problem. I create here on the left side on that cell the bracing again. So first of all, go here to Tools in the menu bar and say Generate Model Members. And at the bottom you find bracing in cells. And the reason maybe why you couldn't create this is because you didn't set the virtual line here. So you see now where are the crosses here, the group crosses. There it's possible to create a bracing. Yeah. Good. But here on the left bottom cell, you don't see that the cross, and this is also the reason why we couldn't create there a cell. In order to do that, we have to create a virtual line in order to close this rectangular by members in order to get a cell. Yeah. I do it now exemplarity. So I click here, select virtual line. In order to close that, I click here from that to that. And then from that node to that node, I click OK. And now the program sees, okay, now this cell is closed and I create here a bracing because now I have there a cross. Now, the next thing is you have to select this cell, click here on the cross or the cell and click on OK. And now the bracing was created. Okay. I think these questions were answered now. Good. I delete this. Now, one important point I want to mention is member of sets or sets of members. In order to combine different cross-section or different members to one member, you can use set of members. This gives you a lot of advantages concerning the loading, concerning the designing, concerning the view of the internal forces and also the interpretation of internal forces. Because now you see here, this whole column is divided into two members. But in reality, on a construction site, it will be transported by one column. And in order to consider that as one column, you can set these members. You can summarize this to one member. And for that, I click on both members, add the upper member also to my selection by pressing the Control key. And then with the right click, I can say, okay, create set of members. And here I can give their name. In this case, I say to the column should be continuous members. And I click on OK. And when I change the display model a little bit to the wireframe model here in the symbol bar, you see here this set of member. And this is very helpful for adding loads there, for designing, for the interpretation of internal forces. I show you now the difference between that one, between the right side, because we have still these two members, and on the left side we have this set of member. And I leave it like that because I want to show you the differences. Okay, so next point is the loading. So you add now some loads. In order to do that, we have to create a load case before. So click here on new load case at the symbol bar. And enter there a name. It's up to you. In my case, I choose the self-weight. I activate the self-weight. Click on OK. And now I add there some loads. Because we are using a frame structure and we have just members here, we have to use also member loads, not line loads. Line loads please use at surfaces. So lines of surfaces or edges. And when you have frame structures, please use member loads. Yeah. Good. I create now a new member load. And I refer to the projected member length. This is similar to the snow load when you have an inclined member, for example. But in this case, it wouldn't make any difference because it is straight, this line or this member. So there will be no difference if you would use to the projected member length or to the related to true member length. Yeah, so it makes no difference. I choose here this one and enter there a value of 12.767 kilonewton per meter. Click on OK, and I choose this girder here. Now I do the same for the slab beam here. Click again on these two members here, but they have the wrong value. So what can I do? I select this like that, yeah. And now you see, okay, I have selected not only these columns, but also these bracings, nodes, and so on. But that makes no difference for us because when I click on the right click, with the right click, I see the different selection options. And this is one big advantage of RFEM, that you can choose of these model datas or load datas and edit them. So in that case, I choose these member loads, uniform, and say edit. And I change the value, so the load parameter from 12 to 68.371. I click on OK, and you see I just changed this member load and nothing else. Good. Now I want to add some nodal forces. For that, I select these nodal forces at the top and say, okay, new nodal load. And because we selected these nodes before, you see, okay, here I have these nodes. Okay, I choose here a value of 40 kilonewton in the vertical direction. So I choose here PZ, click on OK. And now I can easily copy that nodal forces also to the other floor, or to the other level. So I click, for example, here at that node, but copying via drag and drop. I can easily copy that very fast. Yeah, you can see, so there are several options to do that, to insert these nodal forces, nodal loads. And now I select that again, click with the right click again, and now not the member loads, but nodal loads, because I want to change the value. It's not 40 kilonewton, it's 2.4 kilonewton. Okay, good. Next thing is the wind load or the horizontal load. And we created this set of member, so you can understand it as a combined member. And one thing is important, the cross-section of these members for the sets of members, it isn't necessary to have the same cross-section. So it doesn't depend on the same cross-sections. This set of members could or can have different cross-section. Yeah. So when I want to when I want to create a set of member, it is possible to have here a different cross-section and to have here a different cross-section. So it's independent from that. Okay. Now see the difference. I create here again new member load. And first I want to create this on the right side. So I refer to my members, choose here load parameter 2.7. And now also the right direction, in this case to the global X direction. Click on OK. And I choose here every member manually. Yeah. You can imagine if I have there more members, it will be a lot of work. But if I have here the set of members, it will be an easier workflow adding this load because we are much faster. So click here, sets of members, change here the value to 4.32. And now see, just by clicking of one of this set of member, I created the whole load along this column. And this is very helpful and useful because this set of members offers you more advantages, like adding loads, also when you design something. And now we can also see in the interpretation of internal forces or in the view of internal forces. Okay, now we added everything and we can calculate it. So you can click here, calculate all, or click here, show results. And first of all, we see here the deformation. If we want to display the deformation a little bit in a nicer way, go here to the display navigator, go down to the results, and to the area of deformation, members, and choose that the cross section should have a colored deformation, and you see it like here. You can deactivate maybe also the isobands, the separation lines, and now it would look a little bit nicer. Yeah, this is one tip. One of my secrets in order to show that a little bit nicer. And then let's go to the internal forces. So for that, we have to activate the members here. And okay, what I want to show you is, first of all, the bending moments. I think that's pretty clear because there we have a hinged joint, so there shouldn't be any bending moment. When we look to the normal forces, I think that's also pretty clear in the columns that we have some normal forces. And now look to the bracing here. Why don't we see any normal force at this bracing here, at this member? Because when we look back to the deformation, we see, okay, this deformation is set to the global X direction. So we have horizontal deformation. This bracing, this member becomes longer. So I think that's pretty clear that this will get tension forces, and this member will get compression forces because it becomes shorter. And when a tension member gets compression forces, it fails and will not be considered in the calculation. And that's also the reason why there isn't any value of internal forces. Yeah. And here we see, okay, this bracing or this member has positive values, positive normal forces are tension forces. I think that should be clear now. Okay, now, again, one important point is that the connections of the member type, so I double click on one of member, we have here different member types. And this member type beam, this is the standard member type for using or for creating these structures. This is a type where you can transfer all internal forces. So you have normal forces, you have the shear forces, and you have also bending moments. So it's a bending resistant beam. When you have trusses, for example, a truss, for example, is a beam, and at that beam you have at both ends hinges. So at the end of this truss, you wouldn't have any bending moments. Yeah. And the same with tension and compression member types and so on. You have a big choice of these member types. But the most important is the beam, truss, and also this tension and compression. Okay, good. Later we come back also to the ribs, but this is another story. Okay, good. And now I want to show you also the view of the internal forces at a set of member, because this is also a more advantage to do that. So I deactivate that. I change to my wireframe model. And I click here with the right click and say, okay, result diagram. And I see it here at a separate window, the whole internal forces, also the distribution of these forces, also the deformations. I can activate it here. This is very helpful, very useful, because when I want to have the same on the right side of my structure, I have to click every single member, yeah, and then right click and say, okay, now result diagram. And Now I have the same effect, the same situation, but I have to click every single member in order to have the same situation like on the left side by where I just click this set of member and say result diagram. Okay, I think that we have everything concerning this. And now I would say we have time for questions. Praxitalis, are there any questions?
Only one, Daniel. Someone is asking what's the difference between truss and truss only N, only normal forces in the member type option.
Okay, I can show you the difference. Okay, first of all, I show you with the help of the cables. Okay, I think that's the best way to do that. So look, the bracing has have the member type tension, but you have also the possibility to have truss and truss only normal forces. A truss can have along his member bending moments, yeah, but only at the end there are no bending moments. So when you look, I create here a rigid joint, so I delete this member end, but I create here a single beam with hinge joints. So in order to create that, I create here at the member end again a hinge, yeah, and now it's a single beam, yeah. You have no bending moments there. You will see it now of this member, just for this member, okay. Look to the bending moments, and I think that field moment is very clear, okay. At both ends we have hinges, and that's also the reason why we get there no bending, no negative bending moments. And the same situation with that you can create also with the member type truss, yeah. With the member type truss, the adding of member hinges is blocked, yeah, because at both ends you have hinges. Now look to the internal forces of the bending moments. Same situation, same effect. Yeah, I think that's also clear. And now I want to show you with the truss. So for that, I choose here these two bracings, say edit, and truss only normal forces. Now I think the better way to show you is when I activate this at the columns. Here for that. So look to the bending moments, and when you look to the columns, you see there are some bending moments, yeah. And when you don't want to have that, when you want to just to transfer normal forces, only normal forces, click on that member, on that column, create here truss only normal forces. So the program will calculate that column that it will get just normal forces. But these forces can be positive and negative. Yeah, so you can get compression or tension forces. So, but nothing else. So just normal forces, positive or negative. I calculate it. Yeah, and you see no bending moments. Yeah. At the calculation before we had some bending moments, but now there are no bending moments, just or only normal forces. Yeah, and this is a difference concerning these member types. Okay. Another question?
Can you please explain how we can calculate the buckling length when making the unit checks using a stability module?
Yeah. So this is the next thing, doing that, making a buckling analysis. So for that, I change these again to normal beam here. Change this beam again to the beam, and the member start a hinge. Okay, now we have the situation before, and now we can do the buckling analysis. So for that, I click here at RF stability. I consider 4 eigenvalues, so 4 buckling cases. I refer to my self-weight load case. I just have to activate my division for straight members at least at 10th. So the minimum number of member division should be 10. It's up to you, but more than 2 definitely. And the other settings, you can leave it like that. Calculate it. And now you see the critical load factors. Yeah, so the factor where you have to multiply the whole forces, the whole loading, in order to get an instability. But we want to show the eigenvectors. And here we see it. Normally there should be, the first eigenvector should be there, but I can say why this eigenvector is like that. Because there isn't a column. This is a rigid joint here because we have here no hinge. I change this now, I make here a hinge, and now keep that eigenvector as first buckling case in mind. I create here, wait a moment, here a hinge, calculate everything again. And now it's better. So the first buckling case here is this column. So we have here the second Euler case. And this is a local buckling case or a local failing, because you see, okay, just this column will fail at the eigenvector or the critical load factor of 5.81. And then the second will be a global failing. Yeah. And to look to the buckling lengths or critical lengths, effective lengths, click here. And here you see the critical lengths of this. Yeah. And when we look maybe to the when we look to the member number 8, there should we have a member length of the same length like this one. Yeah, look here, member number 8. We have here for the first eigenvector the effective length vectors 1, and this is also similar to the Euler case 2, and this length will multiply by the normal length here, and we get a value of 5.7 meters. Yeah, this is the effective length, so the buckling length. Okay, good. Next question.
Is there a way to determine what is the right cross-section of a member through the RFEM software? How you can choose sizes, etc.
So as far as I understand, this question is
I think
okay.
The design practically.
Yeah, I think so too. So you want, okay, I think you want to prove if this cross-section is enough for the whole loading. In order to do that, you have to do some designs, and we can do a simple design, for example. So look to the, we make a very easy design. We make a stress design here at that beam. So look at the results, look at the bending moments. So we have here this normal forces, this bending moment, and so on. So now look to that. We make a very easy design. For that, you have to use one of our add-on modules. And there you can refer to several design options. For example, when you want to design it according to the Eurocode, please use this RF Steel Eurocode 3. When you are from somewhere else and you use some different standards, please refer to the wished standard here. But for that, I make a very linear elastic proof. So I go here, RF Steel members. This is a general stress analysis of stress members. I refer to that member here. Click on OK. Choose this load case here. Now I can check here the right material and the cross section. And here you have the possibility after the calculation also to optimize the cross section. And I have here this cross section IPE 270. Yeah, I calculate it, and you will see, okay, the stress ratio is okay. So we have a value here of 0.64, and that's okay. So I can go back, say cross section, the maximum design ratio is 0.64, and I can optimize it. Yeah. So the cross section will be optimized, therefore the optimal section from the table will be used. Yeah. So we can get a smaller IPE profile. Click on again on calculation. Now we have another stress ratio. It's much more than before because he refers to the optimized cross section, and this in this case it's the IPE 240 profile. And this is maybe a way to optimize or to get your cross sections, the right cross section for that case. Okay. Another question, maybe the last question of this chapter.
Okay. What are null members? Null elements, sorry.
Null elements. These null elements are members without any rigidity, so with any stiffness. It's just for maybe when you want to model something in an easier way, and you don't want to consider some calculate, and when you don't want to have any impact on the calculation, you can use these members. So for example, I can create here this null type here. Yeah. this beam will look like that. And then I would, for example, have a closed cell, for example. Yeah, this is maybe one option. Or when you want to add a surface load or members and you want to cover the whole right rectangle, you can use this null members. So the null members are maybe one way to model something, but you don't want to have any impact on the structure. So this member types these member types don't have any stiffness and so on, just for easier modeling. Yeah. Okay, then I would say let's go ahead. Or would you say, Praxiteles?
Yeah, I will answer the remaining questions in the chat.
Okay, fine. Thank you. So I prepared some questions for you that will cover this chapter. For that, first of all, this question. Okay, most of you have chosen. I close this poll. Show you the results. So when I have this member type beam, all internal forces are transferred or are transported to the other beam or to the other member. So I have a bending resistant joint. Yeah, no hinged and also no semi-rigid, really bending resistant. Okay, good. Next question is this one. Okay, I close this poll again. So at a 2D system, there are always some rotations and deformations partially blocked because we refer to a 2D system. And now it depends if you are watching a plane out of the plane or in the plane. And that's also the reason why maybe when I modify or I insert some supports, and that's also the reason why there are some rotations or displacements are blocked. I can show it here you again. So I click here on one of this support. When I added this type of nodal support, you see here some displacement and some resistance. So here the supports and the restraints are grooved out, and that's why, and that's because we are using this 2D system, and there is also that some deformation and rotations are partially blocked. Good. So last question of this chapter is this one. Okay. Good, I close this window. Show you the results. And what are sets of members? They must be understood as combined members is the correct answer, because the set of members aren't depend on the same cross-section. So you can have different cross-section and you can use that also as set of members. Yeah. Okay. Good. I see some questions concerning the buckling length again. So there's one question for the exterior columns, how we can calculate the buckling length. Okay. I try to answer that. So here you see this eigenform, this eigenvalue, and when you want to have a buckling length of the whole column, it will not be possible because you have here two different forms. Yeah, so from there to there on the one hand, and also from there to there. So to say one buckling length for the whole column, this isn't possible. Yeah, and when you make buckling analysis for steel structures, you refer just maybe for one length of this member here. Yeah, so remember this member number 4 here. I jump back to the RF stability, member 4, effective length, and this would be the member length you would have to do your stability analysis concerning your steel structures. Almost 10 meters, yeah, and this is important. Sorry, no 10 meters because, no 10 meters because you have also to refer to the right eigenvalue, eigenvector, and this is the second form. Yeah, and for that you would have to use the second form here. So member 4, eigenvector number 2, and there you would have this effective length of 8.5 meters. Yeah. And the effective length isn't the same as the buckling. Okay, sorry. The effective length is the same, like, yes, of course. The buckling length is the same as the effective length. Yeah, this is the same. There are several expressions for that. Yeah, effective length is same like the buckling length. Okay, good. Now we jump to our next project. For that, we create again a new model. Enter their name, concrete model, and refer to a 3D model. I choose the right project name and save it to the right folder. It's up to you where you save it. My z-axis is orientated downwards, and now it's very important that we choose here the Eurocode, yeah, and select here the right national annex. For that, it's okay when we have here the CEN, also the Central Europe, and create the combinations automatically. We click on OK. And a new window will open. And now I show you what we are going to do. We have here several floor plans, and this will be our plans, how we model it. And when I jump back to my PowerPoint, you see here on the right, this kind of structure we will model together. Okay, good. In order to enter or in order to insert the nodes very easily, I would recommend you now to use the tables, okay? So I jump back to the view in Z direction in order to have my WEC window like that. And now I insert several nodes via the tables. Yeah, it's very easy when you have the coordinates in order to do that. So just click here at nodes, click on one row or at one cell, refer to the origin point, then jump from one cell to the other cell with the help of the tab key on your keyboard, and enter here for X for the first node 0, 0, 0. Yeah, and then just click enter, and it will jump to the next row in order to create the next node. Okay, for that we create 14, 0, 0. Next node will be 0, minus 12, 0. And the other node will be 14, minus 12, 0. Okay, good. Now we have these 4 nodes. And with the help of the 4 nodes, we can create easily one rectangular surface. Now, one last node I create. This will have the coordinates 0.5, minus 0.5, and 0. Okay, good. So the next thing we're going to do is creating this rectangular surface. So click here on New Rectangular Surface. And I think this is now similar, so familiar. We decide to create this concrete C3037. And we have a thickness of 200 millimeters. Click on OK and draw this rectangular surface from there to there. Okay, this is our first surface. Now we create here a semicircular surface. In order to do that, I want to create here an additional node to have a radius in order to create this semicircular surface. So for that, click here to the symbol bar, go to a new node and choose here with the help of this arrow, node between 2 points. Now go from the upper right corner node, click on that and go 4 meters downwards. 1, 2, 3, 4. And now you can say, okay, at which distance the new node should be generated. Exactly at the half, because I want to have it here. And you see, okay, here I have now a new node. Good. Now the next step is that we create this semicircular surface. For that, go to the new rectangular surface, click on the arrow, then you have a choice of several forms of surfaces. Here, choose semicircle. Choose also the right thickness, click on OK, click on the radius, and go 2 meters down. And voila, we have this semicircular surface. Okay, good. For the next things, we need to copy, this node several times along this axis, and also copy it a little bit upwards. Okay, so click on that node, click with the right click on move and copy, and say here, okay, number of copies should be 2 with a displacement vector of 5. Click on OK. And the last node I want to copy again, but in this case only once, with the displacement vector of 3. Okay, good. Now I want to copy these nodes again against the global Y direction. So I select every node. Important that you draw your selection window from the left to the right lower corner. Right click, say move and copy again. In this case also number of copies should be 1. And this displacement vector in this case is minus 4.5. Okay, and now you select the third node from the left side. Again, move and copy. And there it should be 4 meters, minus 4. Okay, now we want to copy everything to the next level. So we draw a selection window over the whole structure. Right click, say move and copy. Now number of copies should be 1. And now against the positive Z direction, because we want to copy it 1 to the next level, click here, enter here the value of minus 3.25 meter. And now rotate your window with the help of the control key on your keyboard and with the help of your mouse wheel a little bit, and you have it like that. Okay, good. Next point is creating the opening. So again, I show you the floor plan. Here we have an opening. Here we have an opening, and I want to create it now. Okay. Keep that in mind, that in order to create the opening over two surfaces is not possible. So you can just create openings in one surface. For that, we have to delete these two surfaces. So click here on that line, click on delete on your keyboard, or right click delete line, and the whole surface disappear. But for that, in order to create now one surface at once, we have the possibility again to create a surface with the help of the boundary lines. Select boundary lines. Now set the thickness to 300 millimeter and click on one of this line, and the concrete slab is generated. Okay, good. Now we can create this opening very easily. Next to the creation or inserting of surfaces, you find the openings. Click here also with the help of the arrow to circle, and click here to the middle point and enter there a value of the radius of 1.8 meter. Click on apply, and then you have this opening here. Okay, good. The next step is creating the walls. Okay, the walls are also surfaces. The walls are also surfaces, and you can create an RFEM a surface when you have at least 3 lines, 3 boundary lines. So how can I do that? For that, I want to create here some walls, and also here the semicircular surface. I need additional nodes and additional lines. So how can I do that? First of all, I divide my lines in order to get new nodes, and with the new created nodes, I can create me new lines. So I click on one of this line here, or in that case on this line on the left side. Click with the right, make a right click and say divide line. In this case by distance. And now I look to my line orientation, and in this case it shows me from the top to the bottom. So I say, okay, I want to have it here at the length of 3.5 meters. So the line start should be 3.5 meters. I click on OK. And this node was generated. And the same thing I do also for the other lines here. I click here on that line. Click with the right click on divide line. Say also by distance. And now I refer to the line end. And here I choose, or I enter the value of 5.5. Click on OK. And the same thing again with this line here. Right click, divide line, distance. Line end is 3.5 meters. Okay, good. And lastly, this line here. Right click, divide line by distance. And here I divide the line at the end, 2 meters. Okay, good. Now I create new lines. For that, I create here a new line at the symbol bar. And draw this line from the upper corner node to the lower corner node. Okay, now I have this line. In order to create walls, I need additional line, because then I have 4 boundary lines, and then I can use this function selecting boundary lines in order to create my surfaces. And now see and watch out. This is maybe one of the most useful functions in RFEM, the copying via drag and drop. I click on that line, press the Control key on my keyboard, and move this line from there to that node. And the same thing I do for the other nodes. Yeah. So these will be my boundary lines later for the generation and modeling of my walls. Okay, good. Now I can create me the walls. To do that, go here to the creation of rectangles, select boundary lines, enter there a value for the walls of 200 millimeters, and click here these boundary lines. Yeah. I think that's pretty clear. The reason why I don't do there any wall is at curved lines, plane surfaces aren't possible to create. So for that, you have to use another way to create there a surface, because what we were doing until now was creating plane surfaces. And this is everything possible with that, yeah. But now you see here, we have here a semicircular surface, a curved line. For that, we have to use something different, yeah. We have to use quadrangle. You find it here, the symbol bar, quadrangle, and that's a general 4-sided surface, yeah. Click on that. Also decide here for the thickness of 200 millimeters and click these boundary lines. Okay, good. Now, finally, step for that chapter is creating our columns. For that, I create me here a new single member. So in RFEM, in order to create girders, beams, trusses, and also columns, you have to create members, yeah? So click here on create new cross-section for member start. Decide here for this rectangle concrete cross-section, and we have a quadratic cross-section of 350 to 350 millimeters. Click on OK, and because we were referring to this concrete cross-section, the material was also set to the concrete C3037. Click on OK, again on OK, and draw this member from the lower node to the upper node, and with the right click, close this insert window. So, because now I want to show you again something very nice. Again, the copy function via drag and drop. Select this member here, press the Control key and move it from one node to the other node. I think that's pretty clear. And now rotate your window so that you can select all 4 columns by drawing the selection window from the right to the left side. And now all columns were selected. And now press the Control key again, and you can copy it easily to the next node, to the next plane here. And then this node here, we want to create there again a column, create this here. Okay, now I have missed something. I have to add there an additional wall. So for that, I choose or I select this outer surface here, this outer wall. Again, press the Control key and copy it from there to there. Okay, good. I think we finished this chapter. Praxitelis, now we have time for answering some questions.
Okay, we got the question, as always, if you could show the opening again.
Okay, of course, that's no problem. So, okay, so I delete this opening. I delete also this this line here. And as I said before, in order to create an opening, you have to do that at one surface. And before we had 2 surfaces, so I created here the whole surface. Now go to the symbol bar, click here on New Circular Opening. You find it here when you click on the arrow. Click here, Circle, and click here on the middle point. And now you have the possibility to do it graphically, but because you are working with the wrong work plane, it will not be so easy to do that. So just enter the value of 1.8 meters, click the key Enter, and the opening was created. Yeah? Okay, next question maybe.
Okay, I think that was everything. You can carry on.
That was everything? Okay.
Yeah. We will have time at the end to answer maybe questions.
Okay, good. So now I would continue with the creation of downstand beams. So downstand beams, also known as T-beams. I show you what I mean with downstand beams. It looks like that. Yeah, these are T-beams or also downstand beams. Yeah, look like that. This is a T-beam. And yeah, I want to create this now with you in RFEM. Okay, good. In order to do that, we have to create a new line because, please keep that in mind, in RFEM, every member has a line and every line can have a member. Yeah, so every member consists also in a line. And that's also the reason why when you choose here this line and click on edit, that at the tab member, there is every time a member available. Yeah, so keep that in mind that every line can have a member and every member has a line, yeah, in RFEM. So for that, we create here a new line in order to create our downstem beam. So I click here on new line, click from that node to that node and again to the column here. So, and now maybe you see this isn't straight, this isn't a straight line. It's a little bit linear. Yeah, you see it here. And this is a mistake. So what we can do now, I want to have here a straight line. So I can copy everything. Sorry, not copy. I can select everything on that node and move it to the same level here. Okay. In order to do that, press please the Alt key on your keyboard, because when you want to select this within this surface here, it would not be possible because you would select also the surface. For that, please select the Alt key and draw a window, selection window, please from the left to the right side. Yeah. Now when you rotate the whole thing, you see, okay, I selected the column, the member, and also the nodes. And then say, okay, move and copy. And now say, select 2 points and return the displacement vector. Click on that node and on that node. And you see, okay, we have a displacement vector of -5 in delta x and then also in delta y. But delta x, we don't want to have this, just in delta y. Click on OK. Yeah. And now I made I made the mistake that I copied it and not moved it. Yeah. So I make it, I undo that by clicking the Control key and set. Do that again. Move and copy and set the number of copies to 0. And now I have it right. Okay. Good. Sorry for that. But maybe it was a nice option or a way to show you how you can change something afterwards. Yeah. Good. Next thing is create the downstem beam. For that, select please this line, add to your selection also the next line with the help of the pressed Control key. Right click, say edit line. You see now here the line numbers we selected, and say okay, go to the member tab and say member should be available. Okay. Now we create a new cross section. So the cross section of the downstem beam. For that, we create a new cross section. Click here on rectangle. And we have a width of 200 millimeters and a height of 150 millimeters. Click on OK. Yeah, looks like that. Click on OK. And now I think one of the most important things is when creating downstem beams or T-beams, please, really, please use the member type RIP. Okay. So when you learned something from this training, and at least it should be just one thing you learned at this training, then it should be that you use for downstem beams the member type RIP. Okay. Go to there, edit this member type, and now a new window appears. Okay. And now it becomes very important. What is a RIP? Yeah. A RIP is a member with the integration widths, yeah. And with the help of the integration widths, you get internal forces not only by this member, but also by the surface. Yeah. So first of all, we set the alignment should be on the positive side of the surface. So it looks like that, so that we have a really T-beam. The upper edge of this beam should be the lower edge of this surface. We set our integration width, so the surface, first of all to L8 of this integration width, and select this surface, in this case this one, and the same thing we do for the side 2, also this surface. And for RIPs, the internal forces are determined according to the requirements of the concrete design, yeah, and the stiffness of a RIP member, yeah, results from the member height, yeah, so from the member cross section, and also the surface thickness due to the effective widths. So as a summary, the internal forces in that member include the member forces, yeah, I think that's clear, but also the internal forces of the surface that are integrated with the width B1 and B2. Okay, please keep that in mind. I click on OK, again on OK. And now you see here this downstand beam. And you see, okay, there's an eccentricity, there's a joint, and now you don't have to do that. I just want to show you that when I go to the display navigator, go to the rendering, click here on model, solid model, surfaces, and say, okay, filled, inclusive with edges. You see it here. So the lower edge of the surface equals to the upper edge of this downstand beam. Yeah. So everything is right. It's also realistic. And this is one important thing to know that when you create downstand beams. Okay. Next thing is the creation of an opening at the other work plane. I want to create at this surface, at this wall, an opening because we want to create a window. You have to change your work plane, yeah, because now it isn't so easy to create there an opening, yeah, because you don't have the right work plane where you can refer, so you have to change your origin, yeah. So in order to do that, click here on Set Origin of Grid Work Plane. Click on that and choose here this corner here, this corner node. Yeah, because then we are in the right work plane. We can change the work plane. So to XZ, so go here and say, okay, work plane XZ. And now it's easier to create a window or an opening there. Okay, so for that, you can refer here rectangle, and now it's easier to create their different openings. But you see the snapping points, the grid points aren't so easy to snap, yeah, and they are not at the right coordinates. So for that, I create my nodes. So I go here, click on data, click here on nodes, say create new node. And now it's important that I refer to that point. Yeah. Sorry, this was the wrong. Sorry. This was the wrong insert of nodes. I think the best way to do that is go here to the symbol bar, click on new node, and there refer to the coordinate system Cartesian. Yeah, because this is now referred to the new origin we set before, and enter here the values of wait, I have to look at 5, 0, minus 2.5, and the reference is to the grid origin, and you see here the new node, and create a new node again, in this case 1.5, 0, and minus 1. Okay. And now you can create easily this opening. Click here on new rectangular opening, click on that 2 nodes, and you can easily create your window or your opening. Yeah, this is one point you have to keep in mind. So when you want to modify, to edit, to change, to create something on another plane, you have to change your origin of grid and work plane. Yeah, good. I change it back to my beginning situation. Yeah, and now we have maybe again some time to answer some questions. Dr. Stellis, do you have some questions?
No questions yet, Anil.
Okay. So I go ahead. So good. I create now my surface supports, okay? Because we need some surface supports in order to hold this complete structure, and also some line supports in order to hold here this lines, because there we want to have a continuous foundation. Okay, first of all, the line support. For that, I choose the line, the wished lines, and say, okay, new line support. And here we create a new line support, and we just want to transfer some vertical loads. So it's okay when we activate just the UZ, so the displacement, which is blocked. Click on OK. Click again on OK. And now the surface supports. For that, I rotate my window a little bit in order to select these surfaces here. So I click on that surface. I press the Control key and add to my selection this surface. Now, with the right click on that surface, I can say, okay, edit surface, and say, go to the tab support and eccentricity, and say the support should be available. And there we change, first of all, the units and decimal places, because we are referring to meganewton per meter to the power of 3. So click here on units and decimal places and enter there at support stiffness orthotropy the forces meganewton. Click on OK. These units will change. And now it's easier to enter the values, not so big. Yeah. So there are these kind of spring constants, 10, 10, 100. And for the shear, we have 50 and 50. Yeah. We want to consider one non-linearity. In this case, the whole surfaces should fail if the contact stress in the Z direction is negative. So if it gets tension forces, no tension forces. So this option corresponds to failure under tension. Yeah, this is right. So if the slab is lifting, no more support is provided. Okay, this would mean this option here. And in reality, when you design or when you model these kind of foundations, please consider every time some spring constants. Don't make it rigid. Yeah, this would have a very bad impact on your calculation, and also you will get no good results, because in reality you haven't also no rigid foundation. You have some spring constants in reality. Please keep that in mind, that you enter there some values. Okay, good. I click on OK, then again on OK, and we have created this support here. Okay, good. The next thing is inserting definition of load cases. So we have several load cases to consider. So click here on new load case. And now you see here several tabs, more than at the other project, because we activated at the general data the automatical generation of load combination. So first of all, here we create the load case self-weight. We leave it like that. We activate the self-weight, so the program calculates or considers the self-weight with the help of the geometry and also the own weight of the material, specific weight of the material. Then we create a new load case. In that case, imposed load, and we refer to the action category shopping areas. Then we create again a new load case. For that, we create a wind in the positive X direction, and again wind in positive Y direction. And the same we do with the imperfection. Once in the X direction and the other towards the Y direction, positive Y direction. Good. All load cases are defined. So let's jump to the actions. What are actions? Yeah, we have here 3 different actions: imposed, permanent, and wind. And when we jump to the wind action, we see here this acting. It can be simultaneously, differently, and alternatively. So what does it mean, alternatively? This means that when I would combine two load cases together, they would exclude each other. So there will never be a load combination of both load cases of wind. Yeah, this means this alternatively. So load case 3 will never be combined with load case 4. Okay. When I have it here at simultaneously, this would mean that these load cases would combine with together. Yeah. And differently, if I have there more load cases and I set them into different groups, they would exclude each other when they have different groups. Okay. But for that, I leave it as alternatively, and I jump to the next tab, the combination expressions. There we have 4 existing combination expressions, 1 ultimate limit state, and 3 serviceability states. Yeah. For the calculation of this structure, these 3 serviceability states aren't important for me because I just want to have this ultimate limit state. So I click on one of that on the lower combination expression and click the Shift button and click to the upper serviceability expression and click here on Use. So these expressions aren't used for the calculation. So when I jump back to this ultimate limit state, I can see here the design situation. When I click on the info button, I see here the design situation and how load cases will be combined. Okay. So here, first of all, of course, these partial factors. Then here again, some partial factors. And when I have more than 2 load cases with different actings, I have also to consider this combination factor. So the coefficient for combination value. Yeah, this one, this psi and this gamma here. The gamma is the partial factor and this psi is the coefficient for combination value. Okay, I close this window. What I want to consider is the imperfection load cases. I have here these imperfection load cases, and I want just that they consider with the right wind load cases. Yeah. For that, I say, okay, all imperfection load cases as alternative. So no imperfection would combine with each other. So they exclude each other, but I subject to specific load cases, and I don't want to have that the imperfection towards the positive x direction will be combined with the wind in the positive y direction, because this would be a little bit favorable for the whole situation, for the whole calculation. And I know the most unfavorable situation will be if the imperfection towards the positive x direction will be combined also with the wind in the positive x direction. Yeah. So I exclude them. The same I do for the positive x direction when I have the load case imperfection towards positive y. Okay, I close this. I jump to the next tab, the action combination. Here we see the different action combination. For that we have here, maybe when I jump to the action combination 3, we see here, okay, we have this factor, and this factor, the leading load case, yeah, the leading action. And this is very interesting that you can see, okay, I have here my partial factor and here my combination factor. And yeah, you can see here we have the full partial factor, so 1.5, and every every other acting or every other load acting will have this additional psi. So in this case, this coefficient for combination value. Yeah. And this is also the reason why we have here a little bit lower factor. Okay. Now I jump to the load combination. What is a load combination? A load combination is a combination of all load cases taking into the consideration that we have these partial factors and combination factors. And we combine these load cases to one bigger load case. So when we jump to the load combination 10, we see here, okay, we have the load case 1, load case 2, load case 4, and also load case 6. Yeah. And here also the different partial factors and combination factors. Yeah. Okay. And then I jump to the result combinations. What is the difference between the load combinations and the result combinations? The result combination is a combination of all results as an enveloping result. So you can see the maximum and the minimum of internal forces or general as of results. And yeah, so in a result combination, the maximum and minimum values of internal forces or deformation, support reactions, and so on are determined. Yeah, this is maybe one big advantage because there you have 18 different load combinations and you want to see the most unfavorable results. And for that, the result combinations are very useful because these result combinations consider all load combinations and all results. So all results of the load combinations here in that case. And there you can see the maximum and minimum of the results. Okay, good. So much to load cases, load combinations, and result combinations. Good. Now I would say, let's make the loadings and then we can calculate the whole structure. Okay. For that, first of all, I jump to the load case imposed load because at the load case self-weight, we don't have any loads. So let's begin with the load case 2 imposed loads. For that, I go here, say create new surface load. Say, okay, I relate to my true area, the magnitude of my surface at the bottom is 5 kilonewton per square meter. I click OK. Choose here. I made a mistake, unfortunately. Again, I click this surface here, and then I rotate my work window a little bit in order to click on that surface. And the same I do for the upper surface, but here I have to change the value from 5 to 2 kilonewton per square meter. Okay, good. Now I jump to the next load case. In that case, load case 3, wind in positive x direction. So here I choose this wall, click on new surface load. Of course, I have to refer now to that one, global related to true area, and enter there a value of 0.4 kilonewton per square meter for the pressure side. Now, important thing, now I use line loads because I refer to the edges or to the boundary lines of surfaces. And there you can use line loads, yeah? So click here, select these two lines, click here on new line load, refer also to the right direction, in this case X direction, and here enter the value of 0.65 kilonewton per meter. Click on OK. And the same thing we are going to do for the right side. Yeah. Here I choose again these two surfaces. Click again on new surface load. And for that I click this one, so I relate to my projected area. And for the suction side we have a lower value, in that case 0.25. And I click here these two lines, create here also a line load, and enter here value of 0.41. Okay, good. Now I jump to the next load case, to the positive Y direction. For that I select all three surfaces here, click on new surface load, relate also to the projected area. For the pressure side we have a value of 0.4 kilonewton per square meter. Now I refer to these lines here, new line load, and also here 0.65 kilonewton per meter. So now I made a mistake. The direction of the wind load is wrong. I click again on these two line loads, right click, edit line load. And of course the direction of these line loads was wrong. I refer to that one related to true line length in the Y direction. Now it's right. So you see, it's no problem when you make some mistakes in the modeling, in the load entering, inserting, and so on. You can change it every time afterwards. Okay, now I want to show you something. You can add everything also with the help of the data navigator or with the help of the tables. The same thing like adding these line loads, I want to do now with the help of the tables. So go to the area loads here in the tables. It's the third section here. Jump to the tab of line loads. And there you see, okay, for that load case 4, we have already this these line loads. The big advantage of this is that you have a really good overview of your existing line loads and some additional information like this one. Yeah. So for that, for the suction side, we create now this line here, this line load. So we refer to lines, choose the lines now graphically. Click this line and this line. Click on OK. Now the load direction and the load distribution is the same. The only thing we have to do is entering the right value, and for the suction side we have 0.41 kilonewton per meter. And you see we have now here a line load. Very easy. Good. Now, next thing, the insert of imperfections. So first of all, I refer to my imperfection towards the positive X direction. In order to filter something, I can really recommend you to work with the Views Navigator. Click here to the Views Navigator, and now you just want to see all columns. Yeah, you can select every column. Yeah, you can select every column, and then you can say, okay, show me the visibility, show me these objects, show me the visibility by selected objects. Yeah, this is one possibility, but there's a option where you can do it much faster. Go there, visibilities, activate here members by cross-section, and activate just the rectangle 350-350. And now you see, okay, everything is selected or everything is shown by this visibility of these rectangles. Yeah. Now you can easily select these columns. When I select these columns, I can say, okay, insert at the menu bar, go to loads, and at the bottom you find the imperfections. And then you can say, okay, graphically. And because we selected all these columns, all these members, you find it here also at the at this box here. I refer to my members, refer to the Eurocode 2, and my precamber is 0, and my inclination is 1/200. 1 to 200. I refer to my local axis in Z direction. Now you have to trust me because I know that the local axis is set right. Click on OK. You can activate the local axis of members by right-clicking on one of the member and say local axis. And now you see also the imperfection. I changed maybe the visibility, the display model. Now we have this wireframe here, and you see the imperfections a little bit better. Okay, good. And the same thing we do also for the load combination 6. So the imperfection of Y. Again, we select everything. Click again on Insert, Loads, Imperfections graphically. But in that case, we refer the direction should be the Y direction. Click on OK. And we have here this imperfection. Okay, good. Now, almost everything done. Now let's refer a little bit to the FE mesh. So in order to set some FE meshes, we learned in the first online training that we have here the menu bar, the possibility to do some FE mesh settings. Click on that. Here we see the general target lengths of finite elements. Yeah, it's okay when you use here 0.5 meters. You have to adapt this length of finite elements every time to your whole model. When you're modeling, designing some joints, for example, with the help of the FEM and with the help of FE elements, you have to adapt here the target length of finite elements, and you have to choose maybe a lower value, yeah, so a finer mesh. It's up to you how to use that. I can really recommend also to leave it here like that, yeah, because the presettings are really okay, really good. Click on OK. And now I want to create here an FE mesh refinement here at that node, because sometimes the FE mesh should be modified in specific parts of the model. Yeah, and those are critical areas such as corners of openings. Yeah, for example here, yeah, then we have corners of openings, or also areas with single loads, because there is very realistic or Now I don't know the English word, sorry for that. It can be very, yeah, there can be singularities, yeah. And you want to avoid singularities as good as possible, yeah, because singularities are some parts of a structure where you can't or where you don't have good results, yeah. And for example, we make here an FE mesh refinement. So click on that node, right click, FE mesh refinement, and click New. Create here a new FE mesh refinement, and we apply that to a node, circular. The radius should be 1.5 meters, and the inner and outer length of this FE mesh refinement should be 0.1 meter and 0.5 meter. Yeah. Click on OK. Click again on OK. Now you see here this sphere or this circle lines. And when I show me the FE mesh, so go to calculate, click on generate FE mesh. And now, in order to see it a little bit better, click here to the wireframe. You see here the FE mesh generation. So the normal FE length, target FE length is 0.5 meter. We set in the FE mesh settings, in the general FE mesh settings. And when we use here the FE mesh refinement, you see here, okay, we made an FE mesh refinement, and here is the inner length, 0.1 meter, and it becomes bigger and bigger up to the 0.5. Yeah. And it's up to you how to do that. Yeah. For example, I learned it in that way that at least here you need 4 FE elements in order to have here good results at this surface here. Yeah. So when you want to interpret here some internal forces or some results, I don't know if 2 FE elements are enough in order to get good results. Yeah. It's up to you. So again, here at the corners, you will get probably was the word I was looking for, probably singularities, yeah. Because here you have just one FE element, and along one FE element, the results are calculated. I don't know if you get here good results. So in my recommendation would be that you would do here maybe some FE mesh refinements. Yeah. Okay. Good. So I cancel the visibility mode. Now everything is considered, in my opinion, and I can calculate the whole structure now. So I go here to calculate, say to calculate, and I choose here the result combination, and this is much faster than calculating every single load case and load combination. Click on OK, and the whole structure calculates. Okay, now let's show us the results. I jump to the result combination, click here on show results. And the first thing we see is the deformation. Yeah. Oh, I think the deformation looks really nice, interesting. You have the possibility to see the deformation of the surfaces and also of the columns here. Yeah, you see now we have here this line deformation of these columns of this member. Go to the display navigator, activate at here deformation results, deformation cross-section colored, and you see here also the deformation of the cross-sections. Okay, good. Next thing, members, the internal forces. Look, let's go to the downstem beam and compare the results. Okay, these results look very good. So we have here field moments. Also here this negative moment above over this wall. I think so. By the plausibility check, I think this is okay. Again, to the normal forces of the columns. Yeah, normal forces are pretty clear. Okay, good. So now let's go to the surface forces, surface internal forces. There we have this mx and my. What does it mean? When I deactivate maybe that at that time the local axis of the members and I activate the local axis of the member, you see following. You have here the y direction and here the x direction. And when I show me the mx, basic internal forces, it is along the local x direction of this surface here. Yeah, I think that's pretty clear. Here we have this bending moments. Here's the columns, we have this negative moments. So I think that's pretty clear. You can make a section. Go here, new section numerical, or create section through surface graphically. Yeah, you can do that and then you can watch these results. I make it. I create this section here at the data navigator, scroll down to sections, click here on right click, new section. Give them a name of AA and choose the right nodes I want to have. In that case, I refer just to the, also from one column to the other end column. The section on surface or the projection direction should be the global Z direction. And I refer just to that surface, not to the other surface, because there are the bending moments a little bit different. Click on OK. Now this result diagram will be opened, but for that case it isn't so important. So I close this. I look. Okay. Yeah, this is you see here now I have when I want to look to the sections, you see here my section, and you see there was a mistake because the nodes of the section isn't right. So I added this, set the section again right, should be this kind. Now it should be right. Okay. This will take some time. Okay. Now I have the right nodes. And you see here the bending moment. Yeah. Good. And also some other internal forces, my and so on. Good. Now, next thing is maybe also important, the contact stresses. Contact stresses appear at the bottom surface because there we have, or soil stresses. Yeah. Here we have these contact stresses. and especially at the areas where are the columns, there we have very high context stresses. I think that's pretty clear. Also, you can show you the support directions. So you will see here at the line supports this support direction. When you want to have this distribution of the line supports, just go here to the display, go to the results, support directions, and say smooth distribution. And then you see here this distribution support direction. Good. I think that was everything. Of course, you can show you the values on the surfaces on every FE mesh or total model of all surfaces and so on. Good. There you have different options to do that. Good. Maybe two additional features. We have the possibility, for example, very good for the interpretation of global deformation. When I activate the global deformation, first of all, the clipping tool, you can cut the plane, set a step of 0.5, for example, and then you can choose here this offset, also choose the right plane, and so on. And then you see also every time the different values there. It's very helpful. You can also rotate the angle a little bit. It's up to you how to do that. Yeah. Okay, good. This is maybe a nice feature. And one of my favorite features is when you want to impress someone, maybe your colleague next to you. And when you want to say, hey, look what I have for a nice structure, click the Shift button and the F button. And then it will activate the flying mode. Yeah. And you can fly around the whole structure or around the whole building. Yeah. So with the help of the arrow keys on your keyboard, you can fly around. With the help of your mouse, you can move your camera, and yeah, you can fly around. And with the help of the ups and down keys on your keyboard, you can jump to the next level and so on. If you if you want to increase the speed or the space of this flying mode, just click on plus and minus key on the keyboard and it becomes faster. Yeah, so much to that. Okay, good. Now, this is the end of the whole online training. Now we have a lot of time for answers, not for answers, for questions. Praxitalis.
For answers too, okay.
For answers too.
So, okay, we got some questions here. Just give me a sec. Okay, could you show how to set a local coordinate system?
Again, could you read it again?
Could you show how to set a local coordinate system?
Of course, that's no problem. In order to set a local coordinate system, you can go here with right click, open the context menu, and go here, work coordinate system. And there you have the possibility to create a new user-defined coordinate system. And when I want to refer, maybe I say now to that level here, from there, now from another level. So from there, from that level here, okay? I can say, okay, look to these points here, U, V, W, and I can say, okay, 0. So my first node, so my origin point should be this. Should be, please, this node here. My u-axis, so you see it here, this case, should be, please, this node. And my another node should be, please, this one. So I created this plane here. Click on OK. Now you can enter them a name, unknown, so favorite coordinate system. Click on OK. Click on OK. And now you see here this user-defined coordinate system. Yeah. Maybe I deactivate with the other coordinates. Okay. This is the way how you can create a new user-defined coordinate system. Okay, next question, please.
Is there an add-on to RFEM to design and calculate different ground types?
What are ground types?
I don't quite understand the question either.
Which time?
11:24.
11:24. Okay, wait a moment. Different ground type. So is there an add-on to RFEM to design and calculate different ground type? What do you mean exactly by ground type? Could you tell us this again, this question? During that, I would continue with other questions.
Okay, another question is, what do you mean imperfection in load cases?
So we have the load case imperfection, and just the load case imperfection wouldn't cause any internal forces. But with the combination with some other loads, the imperfection would cause additional internal forces. So you have to consider these load combination, these imperfections every time in load combinations. Yeah. Okay, next question maybe.
Why the supports do not coincide with the column's ends?
Do you know the word coincide?
No, sorry, I don't get the question.
Sorry for that. I can look it up in Google maybe. Coincide.
Übereinstimmen. Okay.
Okay.
I think I understand the question, Daniel.
Do you know it?
Why the blue supports don't align with the columns? But it's really, I think, it's really a graphical thing. It's not that they do not align, it's how they are displayed. I think that's the question.
So when you look to the surface supports here, so this means that at every wait a moment. So this surface support means that on every FE node, yeah, like here, here, and here, and also here at the column is a support condition, yeah. And that's the same also here at the line support. So this column is also held by this support surface support. Okay. Next question.
The ground type for the previous question, the ground type is about soil base.
Okay, I understand. Yeah, there is a possibility to consider that. We have an add-on module called Soil, RF Soilin, and there you can do some soil structure interaction analysis. So you enter your different types of soils, yeah, of grounds, and with the help of that consideration, it will automatically calculate you the different stiffnesses in consideration with the whole interaction of the whole building. Yeah, that's possible. Refer to this RF Solin add-on module. There you can do that interaction. That's possible. Yeah. There are different, in my opinion, there are different calculation methods concerning the right bottom analysis, so the right ground. So consider the ground is a philosophy topic for itself. Yeah, there are different ways to do that, different methods. Yeah, maybe I could. Yeah, there are different ways to consider that. Good. Next question.
Okay, that's a long one. While discussing the result options in the internal forces, you said mx is mentioned with respect to local axis, but in the model we have x-axis oriented differently with respect to different surfaces. How to interpret this result? This question is at 11:59, Daniel.
Okay. These kind of wait a moment. I go back to my right work plane. So you have to differentiate to distinguish between the local axis of this member and the global coordinate system, and the the results of these members refers every time to the local axis of the surface. So when we look maybe to one of the walls here, okay, mx and my, I think that's pretty clear that we don't have there so much bending moments. But when you look to ny, there we have now some normal forces in that in that wall. So please keep that in mind. These basic internal forces mx and my refers every time to the local axis of the surface. Okay. Next question.
Give me a second. Okay, how do you consider eccentricity of loads, for example, in column members?
That's a very good question. That's a really, really good question. I have to think about it because I think that's possible because we implemented this function, but I have to look it up how to create this. Maybe Praxitelis, could you looking for
I can look it up and send the link maybe. Yeah.
That would be fine. Now I think I have it. Wait a moment. Yeah, okay. Look, now I have it. When we go to maybe to the frame there, I hope that this is possible. You find here at the member load here, edit load eccentricity. And here you can do some offsets of the member and the member sets and refer to the right cross section and so on. And there you can consider your load eccentricity. Okay, so you find it here at the member loads and load type force here at edit load eccentricity. Okay, good. Next question.
Give me 1 second because I was pasting the link for everyone to get more information about it.
Okay, thank you very much.
Okay, good. Okay, is it possible to make a kind of a reverse design with RFEM if one has an already existing structure and likes to calculate how much load it can take? The question is at 12:09.
Yeah, that is possible. Yeah, it's similar. It's similar to the RF stability. There you can calculate. So you have this structure here. And now you want to see, okay, how big can my load, how big can be my loads until this whole structure will fail. Yeah, just use the RF stability, look to the critical load factor, yeah, and compare these results, and then you see, okay, this structure is okay and this is not okay. Also, this is possible, but I see this is interesting for recalculating already existing building. Yeah, you can use this RF stability. I would recommend you to do that. And every time you use that, you see also the results. Wait a moment. Yeah, use this RF stability and play with the calculation load factors around. So with the critical load factors, you can also do some external things like here at the self weight when you go here to the calculation parameters, or you can do here some things like incrementally increasing loading. You can activate that and look, okay, at which initial load factor my structure will fail. This would be possible. Or also modify your loading by different factors. And then you can watch, okay, is it okay or not, and so on. This is one way to do that. Yeah, next question maybe.
Is it possible to have cross-section trapezoidal shape in bottom floor?
And bottom floor. Yeah, you have the possibility to create different cross sections, of course. When I go here and when you want to create this cross section, use this cross section library. There you will find a lot of cross sections. Also some trapezoidal cross section, like this one here, trapezoidal hollow section. This is possible. Now I think is what you mean. Yeah, of course, this is possible here, trapezoidal hollow section, in order to have this as a downstand beam. Yeah, that's possible. Now I know. So you want to create maybe a composite structure. Yeah, this is possible, of course. Yeah, so you find it here, material library, trapezoidal cross-section, hollow rib section, or also here, trapezoidal hollow section. Yeah, that is possible. Next question.
Are you going to consider issue of punching shear between the column and the slab surface?
Yeah, of course, there is. You have to consider these things. You can see the values here. So when I look to the results, go to the basic internal forces. I think that's pretty clear. And when you want to design this in consideration the shear punching, you can use one of our add-on modules. And this is RF Punch Pro. Yeah, and there you consider the punching shear design of surfaces and consider these forces within these columns here. Maybe design internal forces would be, yeah. But you have to activate, or you have to use this RF Punch Pro add-on. Yeah. Good. Next question.
The next is if you could show some options related to documentation of results.
Yeah, of course. So, but this will take a little bit longer. So when I want to transfer some results or some information about the whole structure, you can create a printout report. Click here on print graphic. Use, please, this mass print. This is very helpful for creating several documents and pictures. Click here on mass print settings. And yeah, first of all, create here, okay, maybe a mass print of your model, isometric view. then generate graphics of your load cases. Select these load cases here, these 6-1. Choose the right view. In this case, I decide for the current view, and then results. Of course, I select the right result, in this case, the result combination. Now I have to choose the results I want to show me. So in that case, I'm interesting for the global deformation maybe, and basic internal forces, and maybe also the super directions, and maybe also the contact stresses at the bottom plate. Say, okay, I refer to my current view, click on OK, again on OK. Then I click on OK, and then the printout report will be opened. Now I have there on the left side this printout report navigator, a big overview about the model information, and here also the generated model. When you don't like this picture or this image, just click with the right click, say edit, and change that. So in that case, I don't want to see the FE mesh refinement, so I deactivate it, and I deactivate also the FE mesh. And then I can say, okay, go back. And now you have it here like that. When you go to the chapter of loads, you see here the different images of the loading and their load cases. Takes some time. Yeah, very helpful. Here again, the wind, and also the different results we created. Okay. Good. This is maybe one way to do a printout report. Yeah. Next question maybe.
Does RF stability takes also into consideration reinforcement layouts if one uses this tool for RC structures? 1219 is the question.
It's a good question. It's a really good question. Because normally, in order to calculate some concrete structures, so we really with the reinforcements, so you get a stiffer cross-section, stiffer surfaces, and so on. You have to use one of our add-on modules. For surfaces, please use the RF concrete surfaces. For members, please use concrete members and also concrete columns. And normally, RF stability should consider these cross-section properties, especially the stiffness, also of the reinforcement column, for example. This should be normally possible. But in my opinion, I don't think that makes it so a big difference when you have a little bit stiffer structure. But when you want to consider concrete design or reinforcements, you have to use one of our add-on modules. So click here on RF concrete surfaces or concrete members in order to design these members here, in order to consider reinforcements than the column, for example. Yeah. And then you can do again an RF stability analysis in order to get your critical load factors in order to see, okay, where are my critical points of my whole structure. Yeah, and I think this is also good for the last question. The last question is how to see reinforcement details. So for that, I click here on the surface. So for example, I click here, RF concrete surfaces. I refer to the Eurocode, activate this result combination, refer this to this material, concrete C3037, choose the right surfaces, here the general data, and also here the surfaces. And now I jump to the reinforcements. Here I can set the reinforcement ratios, the reinforcement layout, and a lot of other things. Yeah. And then you can calculate it. Also, you can use it, the diameter and so much other things. And then you can calculate it, and then you will see the different results. I don't know if it's now be right and so on. But you see it calculates a long time. So I cancel this. But here you can preset everything. For that, I would recommend you to look our webinars concerning concrete design. And we offer also some online trainings concerning this concrete design. So I think that is everything for now. Or is there any question?
No, it's just one last. If we are planning other webinars like this for other products of Dlubal, like Airstab or some special designing tools.
Yeah. So we offer other free webinars. So me and Praxitelis, we are especially responsible for the basics of RFEM and RSTEP. I can do some steel design. Yeah, that's possible. I can also do some concrete design, but for that we have other employees who are specialists in that areas. And so I would recommend you to look to our online trainings and webinars. So first of all, here at online training and webinars, at online trainings, we offer some trainings, especially for concrete design. Also here for timber design. This is maybe very helpful. So these are the next terms. When you go to the webinars, you see some dates of following webinars. For example, when you are interested in concrete design concerning the Canadian standard, I would recommend you to watch this one, concrete design in RFEM. This is very interesting. And of course, we have a lot of webinars. A lot of webinars in the past. And when you're interested in maybe concrete structures, choose here industry concrete structures. And there you have a lot of webinars in the past concerning concrete structures. Yeah, design of single foundations, for example, concrete design according to the American standard, and so on. This is very helpful. Punching shear design, a lot of helpful information. Yeah, So, of course, we also offer webinar for designing of timber. You can also, when you go to YouTube, and when you add there our software name, Dlubal, and add there timber, you find all possible videos about designing timber structures, some webinars, some short videos. The same when you put there concrete. You will also find some webinars about concrete design, and the same thing also for steel. Yeah. And for the future, we are developing our e-learning platform. At the moment, we just have for English people the RFEM 5 for beginners. But for the future, we are really producing a lot of videos, and we make some online courses concerning concrete, steel, and timber design, where we do, with the help of a lot of examples, a lot of videos concerning these designs in different categories like timber, steel, and concrete design. We will produce it, and when you want to see these kind of videos, please follow us, visit our website regularly, then you get all information you need. One interesting point, when you go here to downloads and info on our website and go here to models to download, you can download a lot of models of our software, and there you see some existing project. Here, for example, this timber round hall. When I stay longer a little bit on that screen there, you see this you see in this structure here, and you can play around a little bit with that. You can watch it, and every model you will find here, you can download it by free. Yeah. Also this reinforced concrete building there, reinforced concrete parking garage, and a lot of other models here. And this library becomes from day to day bigger. Yeah. Okay. Professor Ellis, anything else from you?
I think we've covered everything, Daniel. At this point, I would like to thank you all very much. I hope it was as fun to you as it was for us. In any case, stay tuned because if we are making a part 3, we'll surely let you know.
Of course.
Exactly. Have a nice weekend and goodbye from me.
Yeah. Also from my side, it was really appreciated that you took part in our online training. It was a nice session, and I wish you a nice weekend. Stay healthy, and I hope we will see us the next time. So, see you. Bye bye.